Hello and welcome to our webinar on controlling H2S in your biogas project. I'm Paul Green. I have a biogas advisory business, and I publish content like this under the Biogas TV brand and hold free monthly webinars for their educational purposes. Today, we're fortunate to have three North American experts on biogas digestion and the creation and mitigation of hydrogen sulfide. The agenda is first a discussion about why biogas projects create H2S. Next, an education on how creation of H2S actually reduces biomethane creation, some in situ control techniques, and finally, cost-effective end-of-pipe treatment approaches. You'll get an email tomorrow giving you the web link to download all these presentations. So yes, copies of these are ready. And the video of this will be up on Biogas TV YouTube site next week. First up is Julie Greer. Julie's a research scientist at Six Ring Incorporated, specializing in environmental microbiology. She holds a master's in science from the University of Calgary, where she studied tailing ponds bioremediation. At Six Ring, her research focuses on enhancing methane production in biogas, as well as advancing sustainable 2G bioethanol production. Julie, the floor is yours.
So yeah, thank you again, Paul. As Paul had mentioned, I'm a microbiologist based here in Calgary, Alberta, Canada, for a company called Six Ring. And today I'm going to be talking about really demystifying hydrogen sulfide production. And we're going to do that by exploring the microbial dynamics within anaerobic digestion. So a quick little agenda on just some of the things that will be covered. So a brief overview on the impact of H2S. Talking about the anaerobic digestion process from a microbial standpoint, looking at sulfur in anaerobic digestion and how it gets in there. That's going to lead to the microbial sulfur cycle. Then looking at hydrogen sulfide toxicity and inhibition to methanogens, and understanding microbial metabolism through chemical reactions called redox reactions, and looking at competition of sulfate-reducing bacteria versus methanogens, and then wrapping it up with potential solutions for hydrogen sulfide mitigation. So a brief overview, hydrogen sulfide in anaerobic digestion is something a lot of us are all too familiar with for all the wrong reasons. Four major issues that come with H2S production. For one, H2S poses significant health risks to both humans and animals. It can lead to severe health defects and death. And what really makes it so dangerous is it will desensitize the sense of smell over time, and that's really going to cause some long-term damage. Second issue is corrosion. So as the hydrogen sulfide gas encounters water within your anaerobic digestion system, it's going to form corrosive sulfuric acid. Now that's going to damage the actual system itself, the pipelines, storage tanks, gas collection systems, turbines. All of that is really going to lead to increases in your maintenance costs. Thirdly, the odor. While it doesn't seem like as big of a deal, even at those lower concentrations, that really pungent rotten egg smell is not so great for the appearance and the way that H2 or the biogas is perceived by the public. So this really jeopardizes future initiatives to get more RNG projects down the pipeline. And then lastly is, of course, low gas quality. So having H2S within your biogas lowers its quality and market value. You'll have to spend additional capital to purify it up to RNG. And this is really going to actually lower the energy efficiency of your system. So now that we've covered kind of some of the big problems with H2S, I want to look at the anaerobic digestion process that's going to generate both methane and hydrogen sulfide. So when you have your anaerobic digester, you're starting with the input materials, which are essentially your organics of carbohydrates, proteins, and lipids. These are going to undergo a hydrolysis reaction where they will be broken down further into more soluble organics. These will be things like sugars, amino acids, fatty acids. Your soluble organics are going to undergo a process called acidogenesis, where they will be broken down into acetate, volatile fatty acids, carbon dioxide, hydrogen, and a few other gases. The larger volatile fatty acids, so propionate, butyrate, things like that, are going to undergo yet another step called acetogenesis, where they will be broken down into those smaller components of acetate and the various gases. Now you noticed on the right-hand side there that one of the gases there is the hydrogen sulfide, and this is going to be coming in play with the sulfate-reducing or sulfur-reducing bacteria. So from your acetate, you are going to have methanogenesis happen. Now, methanogenesis is done by a group of methane-producing archaea, commonly misreferred to as bacteria, actually. Acetate is broken down by methanogens, specifically acetoclastic methanogens, to methane and carbon dioxide gas. Now, carbon dioxide and hydrogen can also be converted to methane by another group of methanogens known as hydrogenotrophic methanogens. So you can really see here that this whole process is linked through a kind of a stepwise reaction, and there's going to be all types of microorganisms within this process that are all going to be cooperating and working together. So as you input your feed into your anaerobic digester, what you put in can vary in sulfur content. And actually knowing that sulfur content can help predict the potential for hydrogen sulfide production. So for instance, materials with higher sulfur content, like algal biomass there, for instance, are going to generally produce more H2S compared to those with lower sulfur content, such as something like cattle manure. This is, again, pretty general. There's going to be a lot of other factors that contribute to that. But overall, you can kind of make the assumption with a higher sulfur content in your feedstock, it's going to enhance the activity of your sulfur-reducing bacteria, and that will lead to higher H2S production. So to understand how the sulfur is transformed into hydrogen sulfide, we have to look at the microbial sulfur cycle. So a lot of your materials are going to enter an anaerobic digester containing either organic sulfur or different sulfate and sulfite salts. Now, these different forms of the sulfur are going to be transformed by different organisms. The steps carried out by the blue arrows that you see there are conducted by sulfur oxidizing bacteria, or SOBs. And the processes carried out by the sulfur reducing bacteria, or the SRBs, are shown in the green arrows. So primarily the focus will be today on the SRBs, that second category, just because there isn't any, or there's very minimal oxygen within an anaerobic digester for these sulfur oxidizing bacteria. And the SRBs are going to be the organisms primarily responsible for your H2S production. So now that we know a little bit about the sulfur, we have to look at why H2S is toxic to methanogens. So methanogenesis is inhibited by hydrogen sulfide with the degree of inhibition depending on the concentration, the environmental conditions, as well as the tolerance of the actual methanogenic archaea themselves. But overall, you can kind of make the assumption that more hydrogen sulfide generally means there's going to be less methanogenesis. So this toxic effect comes into a kind of a twofold process. The primary mode of inhibition is going to be an actual competition for organic and inorganic substrates between the sulfur-reducing bacteria and the methanogens. These organisms compete for both acetate and hydrogen. The secondary mode of inhibition is actually going to be from the H2S itself. Now, this molecule is highly reactive and it can actually diffuse across cell membranes. This is going to lower the membrane integrity of the cells and the microorganisms, denature proteins, inactivate enzymes. And this actually doesn't just apply to methanogens, but all of the microbes within your anaerobic digester can be affected by this. So to understand a bit more about the competition between sulfur-reducing bacteria and methanogens, we have to actually go back to kind of a chemistry 101 and look at microbial metabolism and redox reactions. So microbes produce energy through a process called cellular respiration with reduction oxidation reactions. When I say respiration, you can think of this almost quite literally. The way that we respire oxygen, you can think of these microorganisms as respiring different types of substrates. So these reactions always occur as a coupled set, where one substrate is going to be oxidized and one substrate is going to be reduced. And you can see the flow of the energy here with those two reactions. Now, microbes will preferentially use a substrate that results in a higher energy yield. So if you look at this reaction, I mentioned earlier that as we respire oxygen, microbes can respire different things. However, these different substrates will actually have a lower energy value as they're used within these reactions. So as you work your way down this ladder, there's going to be less and less energetically favorable reactions for the microorganisms. However, as each substrate is depleted, the microbes will move down this ladder. So if you wanted to actually put quantifiable values to these reactions, you can look at the redox potential. So this is going to be the energy potential that can be generated from these different reactions through the metabolism. Now, microbes will, as I mentioned, generally prefer more energetically favorable reactions. And this is going to be done by using substrates with higher redox potentials, shown at the top here. Now, that's not to say that the reactions shown at the bottom of this are not going to occur. They're just going to be less energetically favored. But there are dynamic microbial interactions and different factors that enable these reactions to happen. So interactions such as adaptable metabolisms. So microorganisms can actually use different types of substrates, such as nitrate or sulfate. Microbial niche differentiation. So as one type of substrate is reduced in an area, then the next substrate that's available will be used by a different group of microorganisms. Spatial stratification is another one. So this is going to be not as applicable to, say, an anaerobic digester that is being continuously mixed. But if you have a lagoon digester, for instance, what we'll typically see is zones where there are more of one type of substrate being consumed within that system. So you'll see kind of a nitrate, sulfate, and methane zone. And the last one is syntrophy. So just as much as these microorganisms are all kind of competing and trying to consume the different substrates, they can actually cooperate together as well. So for instance, fermentative microorganisms typically pair with methane-producing microorganisms where they're sharing the energy, so to speak. So the products from one group of organisms can be used as the reactants for another group of organisms. So I'm going to bring you back to this anaerobic digestion process. So we kind of got a little bit about the metabolism, about the sulfur, and I highlighted earlier that you can see the gases where the H2S production is going to occur and where the methane production is going to occur. So this is where that competition is going to come into play. So I mentioned SRBs and methanogens will compete for different organic and inorganic substrates. So looking first at acetate, both methanogens and sulfur-reducing bacteria can use acetate as a carbon source. The SRBs are going to use it and it's going to be converted with CO2. The methanogens will use it to convert it to CO2 and methane. Now, the SRBs do have that leg up, so to speak, because they do have a more energetically favored reaction that's coupled with the acetate breakdown. And that is why they're going to kind of outcompete the methanogens, so to speak. Now, the other reaction is through inorganic substrate competition, and this is going to be actually a fight for hydrogen. So similarly with the acetate, the sulfur-reducing organisms are going to have the hydrogen conversion to water coupled with the conversion of sulfate to hydrogen sulfide. And that reaction is going to be more energetically favored as opposed to the methanogens that are going to be coupling it with the conversion of CO2 to methane. So looking at all of this and what we can do about it, there's a few different options, starting with pretreatment. So the first one being very obvious, we're going to avoid feedstocks with a higher sulfur content. Things like algae, grasses, silage, and straws typically do have more sulfur in it. You can also do pretreatments of your feedstock to remove the sulfur compounds, things like acid and alkali treatment, oxidation pretreatment as well. There are processes we can do during the anaerobic digestion to minimize the H2S, so maintaining neutral pH. It seems relatively simple, but methanogens are extremely sensitive to changes in pH, whereas something like a sulfur-reducing bacteria is actually a lot more tolerable to, say, a change in the pH down to an acidic condition. You can also increase the hydraulic retention time of your system. So because methanogens do have that less energetically favorable metabolism, they grow at a much slower rate than sulfur-reducing bacteria. So if you have too short of an HRT, it may not allow quite enough time for the methanogens to produce that methane. You can introduce additives like iron scavengers that are going to react with the H2S. However, this could be even introducing another problem in itself, because if you remember from earlier with that substrate ladder, iron is one of the substrates that microorganisms can use. So you might be introducing another problem while trying to solve another. And the last is microaeration. So this is really going to be introducing oxygen to promote the sulfur oxidizing bacteria. Post-treatment processes, obviously these are done quite a bit, where you're going to be chemically treating the biogas through alkaline scrubbing or oxidation to remove the H2S. You can use absorption techniques with activated carbon, or you can pass the H2S through a biofilter, which actually contains the sulfur oxidizing bacteria that will convert the H2S to elemental sulfur. So the two I kind of really want to hone in on are the pre-treatment option and microaeration, just because these are really tackling kind of the heart of the problem, so to speak. So pre-treatment is something that we actually do here at Six Ring. So we take waste biomass, things like agricultural waste, forestry waste, and put it through a reaction that we call a delignification. This is going to be taking the biomass and breaking it down into two primary constituents, one of which is going to be a very high purity cellulosic product that we call stimulose, and the other of which is going to be a liquid product that we call LHDO, or lignin hemicellulose depolymerized organics. Now, the beauty of these two products is you can use both the cellulosic product and the LHDO, which can actually be upgraded to bioplatform chemicals. So if you were to start with something, say, like a canola straw that has a sulfur content of 0.35%, and put it through this delignification process, you get this very high stimulose product that actually has a sulfur content of 0%. So you're effectively removing the sulfur and thereby going to be preventing a lot of that activity from the sulfur-reducing bacteria. Now, a lot of biomass pretreatments typically involve high temperature, high pressure reactions, but the beauty of our technology is it occurs under ambient conditions, so room temperature and pressure. And the chemistry that we use, we actually recycle all of the chemicals. So going from 0.35% to 0% might not seem like a significant change, but when we did test this in a 20-liter scale reactor, what we noticed is that there was actually a decrease on average of 54% lower hydrogen sulfide concentration in this test reactor compared to the control when we replaced an equivalent amount of the stimulose compared to a canola straw. Now, the beauty of this as well is you have a very high pure cellulosic product, as I mentioned, and that's going to be a very readily bioavailable carbon source for the microorganisms. And when we also observed this hydrogen sulfide decrease, we actually noticed also an increase in the methane volume production in the test reactor compared to the control. So the last pretreatment I wanted to briefly touch on was microaeration. So this is not something here we do here at Six Ring, but it is one of the few solutions that really tackles the part of the problem by looking at the redox and the metabolism of the system. So introducing very tiny amounts of oxygen will inhibit the SRBs from reducing the sulfate to H2S based on that redox ladder, and it will actually promote the sulfur oxidizing bacteria to oxidize the H2S to elemental sulfur. Now, this method is very tricky because there's a very small window in which the conditions are optimal for the sulfur oxidizing bacteria, where your pH needs to be pretty much perfectly neutral between 6.5 and 7.5. And the overall optimal redox potential of your system, which you can actually measure with a ORP probe, needs to be negative 250 millivolts. So it needs to be a very highly reducing environment. The injected oxygen that you're inputting needs to actually be immediately consumed, so the anaerobic conditions are maintained. If you inject too much oxygen, you're going to actually cause a lot more damage to the microbial community. So that does make this treatment an operational risk factor. but it is one of the few solutions that really tackles the metabolism and redox of the system. So just to summarize everything that I went over, overall anaerobic digestion is a complex process driven by a very diverse microbial community. Microbes work in synergistic interactions where the products of one group serve as substrate for the others, and this is what's going to enable that efficient organic matter breakdown and biogas production. There exists a competition and a cooperation between the different microbial groups, and this balance of competition and cooperation is going to determine the composition of your biogas. Sulfur-reducing bacteria in particular compete with methanogens for both acetate and hydrogen, and SRBs have that more energetically favorable metabolism, which is really going to give them an extra boost and more favoritism in terms of producing hydrogen sulfide over methane. And lastly, and probably most importantly, understanding the biological processes behind hydrogen sulfide production is going to help identify its root causes and develop those targeted solutions to mitigate the effects on anaerobic digester systems. So thank you all so much for your time. If you want to contact me about 6-ring or H2S or looking at microbial dynamics within anaerobic digestion, feel free to reach out.
Thanks, Julie. Appreciate it. Awesome job. I'm still amazed the more I learn about, when you put sulfur into a reactor. I used to just think it was an H2S scrubbing problem, but the notion of it being something that reduces your biogas yield because the SRBs are soaking up all that carbon. I'm still wrapping my head around all this. So great job. Thank you. Moving along here, today's webinar is brought to you by Galton's Green Technologies. So next time you're looking for a fantastic self-performing mechanical and electrical installer for your biogas RNG projects, be sure to reach out to Galton's. Galton's Green Technologies is competitive in all 48 states and has a fantastic biogas RNG resume. Find them at goltens.com/services. Next up, we have Tim Oleg. Tim is the biology manager for Plant ET Biogas based in Lucerne, Colorado. He manages Plant ET Biogas's digester health lab and provides operational guidance to clients operating co-digestion and manure-only biogas plants in North America. Tim's helped clients develop optimized control of H2S and raw biogas through efficient dosing of micronized iron powder into substrates and digesters. Tim, thanks for joining us today. The floor is yours.
Thanks, Paul. Happy Friday, everybody. Today's focus for my presentation is going to be that in situ or that in digester iron addition that Paul mentioned earlier. We're really looking to help clients get a good handle on the H2S that's generated in the digester to really protect downstream equipment, help with the RNG process, help with other desulfurization technologies that might be part of a larger biogas process. So that's going to be the focus for me today. First topic is going to be the benefits. Why are we even adding iron to the digesters? What's the whole benefit of doing that? Two major iron options. There are a lot of different kind of little tiny variants of iron out there, but we want to look at the pros and cons of at least the major ones today. If you have questions about some of those other variants out there, happy to talk about them. There are a lot of good options for iron addition, but I'm going to make the case for one in particular, and then happy to discuss if you ever want to look at kind of the details of what might work best for a particular system. Going to look at common pitfalls for iron addition, including some of the things that might get overlooked or cause some major roadblocks with the iron-based H2S treatment. Some very important things to think about. H2S treatment thresholds for raw biogas. What are some kind of common target levels or levels of value that we should be looking at with iron treatment? Factors that could affect the required iron dosage. Want to think about things. I mean, it's a huge list of things that can play into not only the generation of H2S, some of the things that Julie talked about in her presentation, but then what kind of factors affect how effective the actual iron ends up being in the digester or upstream of it. Some very important things to think about with that. Then make the case for the dose response approach for optimized dosing. Dose response is something that comes out of kind of the pharma world. We kind of use something similar to that. We want to see what's our actual sustained effect over time with a nominal dose rate of iron. How do we kind of lock into a good, at least baseline dose rate to make sure that the iron's both, effective enough to keep the H2S down, but also cost efficient. We don't want to overdose a bunch of iron, not only for cost reasons, but also potentially, if it's bad enough, for potentially some chemical reasons as well. So dose response, going to talk about that a little bit. And then the major iron solution that Planet provides for indigester H2S treatment is going to be Micronox ON16, a micronized powder that's very effective when it's applied the right way. So starting with why, big thing is it's treating H2S generation at the source. As Julie pointed out, we have that sulfate transition to H2S in the digester. We want to have a good capacity to reduce H2S in situ in the digester so we don't have quite as much work downstream with carbon tanks, biological desulfurization, chemical desulfurization after the digester gets going. So very important to for many people out there. I mean, it really just makes sense to treat H2S effectively in the digester before taking a lot of the remaining H2S downstream of that. It can prolong the life of equipment, especially stuff that's susceptible to H2S corrosion or that sulfuric acid corrosion that Julie mentioned. Activated carbon and other media, we want to prolong the life of those. We can very quickly burn out things like activated carbon if we don't keep H2S levels under control in the raw biogas. So huge value there, treating H2S at the source. Biological health, a lot of this stuff, coming back again to what Julie mentioned, Julie did a great job talking about a lot of this aspect here. H2S toxicity is a really, really big one. And there's also this ongoing balance between those SRB, the sulfate reducing bacteria, and the methanogens over time. It's just kind of this constant war in the digester there. So we want to bind sulfur, we want to treat H2S, we want to keep those methanogens very, very happy so they don't have a difficult time trying to keep up with the SRBs that could kind of win the war from time to time and create these big blooms, these big spikes in H2S. Iron is very important for enzyme production, other biological mechanisms in the digester. So we also kind of need it at a baseline concentration for that. And also a really big part of this is, and some of you probably heard of trace element, the importance of trace elements for different microbes, including methanogens. We want to make sure there's plenty of iron to bind sulfur that could steal away some of those trace elements or make them unavailable to microbes. So iron does a very good job of binding sulfur and keeping those trace elements available for really important biological activity in the digester, including methanogenesis. For people who have issues with struvite formation, it can be a huge pain point for clogging up pipes and other equipment. It can bind phosphate and reduce the formation of struvite, so that's a big value add. Can enhance dewatering potentially through coagulation and flocculation in certain applications. And then it's potentially, kind of depending on the situation, it can be more adaptable to process changes than other treatments. It can just be dosed at a varied rate to keep up with H2S in a fairly timely fashion. First solution I'm going to highlight is ferric oxyhydroxide. You'll also hear this called ferric hydroxide or iron 3 hydroxide. Main thing here is we've got a ferric-rich powder or a granular form. It's going to be added either upstream or directly to the digester. Pros of this one, not corrosive, safe to handle. There is potentially some powder and some stain kind of risk. You want to be careful. You don't want to breathe this stuff in, but otherwise it's not going to have any kind of corrosive risk like ferric chloride would. And you can apply it by hand in very controlled amounts or machine if you have a good mixing system and good ability to inject kind of in a good dosed form. And a big one is it's kind of as a moderate reaction rate. It's not initially soluble. It's kind of kept in a suspension in the liquid or the substrate. And over time, kind of keeping that moderated iron concentration in the digester, it'll help buffer against H2S spikes that could pop up as certain feedstocks come in, or you have sudden changes to the biology that could result in increases in H2S. On the con side, really important, you need to keep it mixed into suspension. Many folks have had issues with it dropping out if they add it way upstream of the digester, like if you have a big stagnant manure pit that's not really mixed well, if you have other types of substrate, kind of liquid pits that just don't get mixed very well. It has some weight to it. It's not initially water soluble. It'll eventually solubilize and react with iron, but you do need to keep it in suspension until it has a chance to react with sulfur in the digester. So very important thing to highlight there. You need the right equipment, or at least the right addition point, to make sure it's going to be effective in the digester. If you don't have a dry feeder or a feeding pit, which some of those can be right next to the digester, they can be great ways to get this powder or these granules into the digester. You're going to need a kind of a dedicated, at least a small scale mixing and injection tank that's specifically designed to get that ferric oxyhydroxide into the digester. And then the granular form can be slow to react, kind of depends on the surface area to volume ratio of that iron. But oftentimes it's going to be preferable to have a powder. It just makes, with the surface area, the ability to get it into a mixture, it really increases the chance that it can get effectively transferred into the digester and reacted with sulfur in there. Ferric chloride, very common treatment. Pros side does react very quickly with H2S, very soluble in water or liquid, and that as a liquid solution, it's ready to inject. Really need to highlight the corrosion risk here. A lot of safety equipment required to really do this well. Things like eye wash, safety showers, making sure you have good chemical containment if it happens to spill from its IBC tote, if it happens to leak from any plumbing in the system. Need to be very careful and really think preemptively about what this is going to look like in the scheme of a biogas plant, because we've seen plenty of examples of major leaks, huge pain point, cleaning this up. There have been some safety hazards associated with that. So really need to think about kind of managing the corrosion from the acidity. It forms hydrochloric acid when it's mixed into solution. So keep that top of mind. Just you're going to need to have good equipment, good forethought around that. There's a cost, of course, associated with that. And I mentioned the spills and leaks can be a major safety issue. But this one can really make sense in certain applications, especially if you need just kind of a ready to go liquid dose for certain applications. Common pitfalls. I mentioned that risk of adding too far upstream. Ferric chloride can precipitate out, form different precipitates with chemicals, kind of depending on the pH and what's contained upstream of the digester. So you can lose ferric chloride upstream. You can also lose ferric oxyhydroxide if it happens to just fall out of suspension, if it's not mixed well, if it's not pumped well. Those are big ones. And that kind of ties into the next part. Many examples we've seen out there where this general iron addition, this need for this in digester H2S treatment is considered way too late in the project. And you can catch up. I don't want to be negative about it. I mean, there's definitely hope to catch up and get a good system in place, but it just becomes much more painful kind of retroactively trying to catch up and get a good iron dosing system in place, at least for many people. There are situations where you've got an easy setup, an easy way to get an iron treatment in there, but you do need to usually think fairly early on, equipment cost, what's going to be that kind of the operational scheme, how are you going to get operators to keep an eye on this, dose it out effectively, measure H2S effectively, some thought around how are we going to track this to really make it a good H2S control solution for the digester and the larger system. So I highly encourage you to think about this early on, at least a number of months before the project's meant to go online, hopefully earlier than that, but very key point. I really want to point that one out. I mentioned lack of consistent monitoring a little while ago. This is a huge one. A lot of facilities will just kind of initially, say I've got H2S controlled, I've got a dosing solution in place. Now we're good to go. We've got kind of an estimated rate we need to dose of powder or ferric chloride. But you really, whether you're in good times with H2S or very bad ones, you really at a minimum need to be monitoring H2S at least once a day and trending it over time. And ideally, you're measuring on a continuous basis throughout the day to kind of see maybe some of those hourly or minute by minute trends. But even for some folks, they've had issues even monitoring on a daily basis, and that really spells trouble for cost efficiency and effective H2S control over time. You want to get a really good sense of what's this particular digester, this set of digesters doing as far as biology, H2S generation, what that particular substrate getting fed in is actually doing, winding up as H2S. You've got to think about the kind of things that can change over time, and a lot does change over time. So highly encourage some kind of, at least a spreadsheet, some kind of monitoring program where you're tracking iron dose, the amount of iron applied, the H2S levels, kind of the response to that over time. Very important to have something in place to keep an eye on that. Then for the treatment strategy, just need to have some type of general strategy in place. There's lots of great expertise, lots of great literature out there. Generally, advise keeping it simple if you can, but at least have something in place, something documented, a standard operating procedure about at least how we're going to monitor H2S, apply iron, what else are we going to be looking at in the system to kind of make sure things are happy and congruent from an H2S treatment point of view. Two key kind of treatment thresholds I'll mention. We usually recommend about 500 ppm threshold if you're specifically looking to protect the activated carbon that's downstream of the digester. Can have great expansion of the lifespan of that carbon by keeping the H2S under 500 ppm. Not a big deal if it happens to spike over that, but just kind of on an average or continuous basis, we're trying to keep usually that H2S under 500 ppm for the protection, the optimization of that activated carbon's lifespan. 1000 ppm, H2S toxicity in the digester. This is one Julie mentioned. Toxicity is a big deal for those methanogens because it can get progressively worse as you get H2S toxicity issues around 1000 or more ppm, starts to really discourage the growth and the metabolic activity of the methanogens, and now the sulfate reducing bacteria have the chance to outcompete the methanogens for acetate. So this is a really important one to highlight. I'd say there are exceptions to this general 1000 ppm level. It's going to depend on other factors, but this is kind of a fairly typical kind of recommendation for keeping that H2S below 1000 ppm to avoid toxicity issues. Dosage range, this is as far as just in the form of ferric iron atoms, so 1.3 to 4.5 pounds for every pound of H2S. Any supplier of a product, whether it's ferric chloride, ferric oxyhydroxide, etc., should have some type of recommendation for what that dosage rate of their particular product is for a given amount of feedstock or a given amount of sulfur or H2S. So start there, definitely start with that recommendation, and it will definitely need to be adapted to your particular system, but always seek that information early rather than late. Try to get some at least recommendation for what that dosage rate should be for your particular substrate and system design. Manure is often going to require more iron than other substrates. Julie got into this a little bit, but there's definitely exceptions. There's going to be substrates out there that just have a heck of a high sulfur content. Could be local farming conditions. Could be the domination of certain substrates in that overall feedstock. But you'll often see a little bit higher requirement on average for manure with high sulfur coming in. And as I mentioned, contact the supplier for initial dosing recommendations, and kind of what I'm going to be getting into next is optimizing that dosage after that starting point. Factors that affect that required iron dosage, we have that treatment goal. This is going to be facility dependent. What are we trying to achieve with H2S treatment? The form and concentration of iron, how effective it is at the particular location that you're adding it at. Want to make sure that we're getting it into the digester effectively, but if we're not, that could greatly expand the amount of iron required to get it in and reacted with H2S. And then that mixing efficacy at the addition point within the digester. Substrate quality and feed rate, we could see some H2S kind of formation lag behind that initial feeding. It does take time for sulfate to form and get converted into H2S in the digester, so there's a time factor there. pH, kind of that equilibrium between H2S and other forms of sulfur. Temperature, including the stability of the temperature. Plenty of cases where you have temperature fluctuating in the digester and the methanogens are not as happy. The sulfate reducing bacteria can outcompete in certain cases, so that will affect how much H2S forms and how much iron is required. Microbial presence and activity, again, that population of methanogens versus sulfate reducing bacteria. Presence of desulfurization bacteria in the digester headspace. This is part of that micro aeration, at least one option as far as micro aeration solutions that Julie mentioned. So we might need to figure out how much do we want to treat in the digestate versus in the headspace. Big star highlight on this one, this dose response approach. So I mentioned starting with that recommended dosage with some good consultation, a little bit of research on how much should we approximately start with for our new system here with its given substrate, its given conditions, kind of the maturity of the digester, how far along is it with its microbial health and its methanogen activity. So we're going to start with that estimated iron dosage. We want to keep it steady. We're trying to kind of build some data here to see what is the actual response of H2S to this sustained iron dosage. And to make that happen, we need to make sure we have at least daily measurements of H2S, at least daily measurements of iron addition, in addition to your other kind of health parameters, things like pH, temperature, methane. We really need to have at least some kind of, hopefully a one-page review or some type of nice overview of what's happening day to day in this system and what's that dose response effect between iron and H2S. So we need to have some kind of data compiled somewhere we can look at all this together. We want to gradually adjust that nominal dosage rate over time. It's going to be a gradual effort until that H2S is right at or right below that target level. And this is kind of the interest, both catching that H2S and making sure it doesn't, we don't have cost efficiency issues. And we want to continue to record H2S levels and iron treatment quantities daily. So this is the Plant ET solution. We have Micronox ON16. I mentioned it's formed as a micronized iron powder. We've had a lot of success helping clients with indigester H2S treatment with this. We can help you figure out what that recommended dosage is depending on substrate, system design, etc. And one of the really exciting things we've got recently, we've released our own version of a mixing and injection tote for direct injection either into manifolds or directly into the digester. And we can really work with your specific system design to make this a good, effective solution for your particular system. So please do reach out. You're welcome to reach out to me. My email's at the bottom left of this screen. And then our Plant ET Biological Service can be reached at the phone number here on the screen and lab-na@planet-biogas.com. This will all be in the presentation that Paul sends out, so no need to furiously write. And I will turn it over. Thanks all.
Thanks, Tim. So one question for you before we move on. Any concerns about iron settling into digesters with this approach?
That's kind of the key thing there is that consistent and high strength mixing. We want to make sure that the digester itself has adequate mixing to treat that H2S. So that can be something we kind of consult with a client on as far as what does that kind of mixing scheme look like? Do you have kind of some engineering data around what that mixing profile is? And we can definitely look at efficient ways to help out with that if there are some mixing concerns.
Okay. Thanks,
Yep.
Tim.
Sure.
Appreciate it. So next up is Timur Dunayev. So Timur Dunayev, PhD, is the Managing Director of POC North America, one of the leading technology brands in the digester biogas space, where he's responsible for all of POC's business, including managing digester biogas scrubber sales and operations. So with that, Timur, the floor is yours.
First of all, thank you very much to Tim and Julie. They absolutely set me up for success on delivering my presentation as well. I also thank you to the mastermind behind the presentations altogether. Paul, I can clearly see the progression here, and I love it. My background is engineering, and there is no tool that fits all the solutions, and I love to see the progression of the tools here. And it's definitely, you can definitely see that there's many applications and different approaches. And when you're evaluating something that is specific for your solution or for your application, it's important to know what you can work with. And so while Julie presented sort of on the pre-treatment side of removing, using the pre-treatment and the lignin removal, so the sulfur is not making it to the system, I think Tim did an amazing job of what to do if you want to handle sulfur and bind the sulfide in the reactor itself, which is definitely a solution you might want to consider depending on the concentrations. I'll be talking about Thiopack system. And the way I would approach it conceptually is, let's say you chose for one reason or another, the sulfur concentration is too high, or there's other concerns with the capital performance or the operational expenses. And then in the end, the biogas concentration, but the H2S is getting reduced. The sulfur, sorry, not the H2S, the sulfur is getting reduced inside of your system, inside of the anaerobic system. It gets transferred into the biogas. And so what you can do once it's already in the biogas phase is what I will be presenting on. The Thiopack technology was developed by Bucks in the late 90s, and since late 90s has been implemented throughout the world. We are using a two-step approach where the first step is basically chemical scrubbing of H2S from biogas. However, the second approach, which is going to be probably the most important core of this presentation, is the biological regeneration of your caustic and oxidizing sulfide once it's binded into the solution in the chemical scrubber into elemental sulfur. That then is a stable product that could be used in many different ways. I am going to skip this slide because Julie did so much better job than this. This is sort of a nod into what H2S is and what it is, but I think there will be no new information here following Julie's very detailed presentation on this. And the H2S as a technology is basically a three-stage approach. So in the first one, as I summarized, what we have is a scrubber. And the entirety of the removal of hydrogen sulfide from your biogas happens within the scrubber itself. It's a countercurrent, free-flowing packed media scrubber where you're creating large surface area to generate effective mass transfer from the biogas phase, from gas phase into the liquid phase, and it happens under elevated pH conditions, and resulting in the treated biogas coming out from the scrubber. Once the sulfide is binded into sodium sulfide, it gets transferred into the bioreactor where we create anoxic conditions, keeping the ORP relatively low, let's say at negative 350, generating mixing and limited oxidation in order to convert sulfide into elemental sulfur. And in that process, the sodium and the hydroxide ion are released back into the system and can be reused and recirculated to continuously scrub your biogas from H2S. And then the elemental sulfur is removed from the system, and we have many different approaches how we remove the sulfur slurry from the system depending on the size and the loading. You can use conventional settler, elemental separators, and in a larger system, even use the decanters to be able to take out sulfur as a concentrated sulfur slurry cake. And this is an overall picture of the step-by-step, but every single time you will be seeing a Thiopack, the core of this is going to be basically the two vessels of the scrubber and the bioreactor and the ancillary equipment related to it. In the field, besides that, we are providing fully skidded or fully containerized system where we combine the ancillary equipment that I mentioned, recirculation pump, instruments, controls, your HMI with the SCADA, all together inside of it. And so it can be part of an existing building. If it's a separately standing system, it could be fully containerized. Since the microorganisms are naturally occurring. There is no need to bring new catalyst into the system. So the biocatalysts are self-growing and self-regenerating. So the only thing that is necessary is a relatively small amount of water to keep the TDS in the solution, or the conductivity of the solution, below the saturation point, and relatively a small amount of caustic that needs to be added, and it's disproportionately smaller than what you would be using if you would be applying as an exclusive chemical scrubber, because caustic is continuously regenerated. You just need to supplement a little bit that will be coming out with the sulfur cake and the rest of the solution. The sulfur that is produced is then the biological sulfur in the elemental form. It's completely stable. Actually, once it's converted into elemental sulfur, it's one of the harder pathways of converting it back to sulfate or sulfide because of the stability of the elemental sulfur. And so what you get is a very, very stable, odorless slurry of elemental sulfur together with some microorganisms. It's non-hazardous and could be disposed of in many different ways. So the advantages of the Thiopack is extremely high removal efficiency, and I'll show some of the case studies, but we can consistently meet less than 25 ppm of H2S, even with extremely high H2S coming in. We're talking about in some oil and gas applications, concentrations of up to 30% of H2S in the gas flow. Very low operational costs, because as I said, the caustic consumption is only there to replenish what's coming out with the sulfur cake in the makeup water. Very high quality of biogas, no additional oxygen in the biogas addition, because the entirety of oxygen is added inside of the bioreactor. So you're not adding oxygen in your chemical scrubber, which is important for some of the RNG system. And an extremely high uptime at 99%, because there's only two moving important parts there, both of which could come in duplicates and triplicates depending on the sensitivity of the project. And that is the recirculation pump that's recirculating the liquor around the scrubber, and the blower that provides oxygen inside of the bioreactor. So the applications are very versatile, and we can control the effluent of the H2S from the system by properly designing the column. But as I said, we can go as low as 25. And so depending on what you are using it for, boilers, CHP, RNG, or other uses, we can go as low as less than 25 ppmv. The systems are extremely versatile. The smaller systems that we have handle as low as 10 kilograms, 22 pounds of sulfur per day. And the largest system that we have in the world is 22,000 kilograms. So 44,000 pounds of sulfur per day, which is a tremendous H2S load. As you can see, that biogas scrubber is massive. And actually, the bioreactor is a massive built-in bioreactor. So instead of a modular system, it had to be built on site. So the versatility on the sizes is quite impressive with the Thiopack technology. It's we have standard sizes and designs, flexibility, and the flexibility there on the skidding and the installation. Most of the time for the RNG applications here in North America, we literally deliver not more than 3 large parts, which is bioreactor, scrubber, and then container or skid are 3 things that arrive on site, and all you need to do is mount them and provide interconnecting piping, and everything else is basically done. The North American business unit is self-functioning business unit with full project management services and the supports, so we can provide continuous monitoring, troubleshooting, and support post-project delivery as well. As I summarized in the beginning, this has been over 30 years in the market. We have more than 325 active references with more than 60 references in North America. Majority of them are in RNG sector here in the United States. Worldwide, the installations are in very different places, and I'll go over a few examples, but I think the most pertinent ones are landfills and RNGs here in North America. Here is a landfill application in North Korea, 50 landfill gas, and that's the biggest installation that we were talking about. 10 tons of sulfur per day being in full operation since 2010. And there is a lot of published scientific articles on this installation out there, together with Eco Energy. Another smaller landfill application since 2001, continuous operation, 40 kilograms of sulfur in Amsterdam, Netherlands. Gas to grade upcycling and sulfur recycling. I like to give this example because here they're also commoditizing and selling their sulfur cake to the third parties at 2.5 tons of sulfur per day. And here's a beautiful example here from United States. There's a California digester, a cluster of digesters delivering RNG, continuing operational loads from 35 to 1,000 kilograms of sulfur per day. And I think we're actually also on time, so I'm not going to be spending more time summarizing things.
Very
I think
good.
that was, and I saved there by 3 minutes to give a little bit of time for questions. Right.
Thank you. Thank you. I love that one photo, Timur, of the California dairy project. So I'll put in a plug for Biogas TV. If you go to Biogas TV on YouTube, you'll see an amazing video we did for a testimonial for the Thiopak at a dairy site. So
that's that dairy site, by the way. So so people can watch a few beautiful video. Paul plugged it in for himself, but I highly recommend it. Paul did an exceptional job with that one.
So a couple of questions have come in. One is on good means of measuring H2S inside of a digester. How do you do that? What's a good way to, as we check H2S, usually I guess think it's on the gas coming out, right? If you want to monitor H2S inside of a digester, how would you do that?
I think I'll jump in, and then I'm sure Tim will provide a little bit more. There's two basic approaches. You can measure sulfide concentration in the liquid phase, but I think more generally people are concerned with the biogas phase, and there you can use Draeger tubes and or gas chromatographs. Very important to select proper chromatographs. Usual GCs don't work. You need to choose proper sulfur column, ASTM 3501.
Yep, agreed. And as it pertains to the stuff I was talking about, as far as that raw biogas H2S getting produced within the digester, in that digester headspace, a lot of good, relatively accurate H2S handheld meters out there that can pull from a sample port up on the headspace of the digester. A lot of good sensors coming out these days, things like Sulfilogger that can go, with that hazardous area certification, monitor H2S in real time as well. So lots of good options out there. Just kind of depends on budget and what installation locations you have available.
So last question of the day, Ganesh asks, which is cheaper, to use iron inside the digester or Thiopak outside the digester?
Ganesh is definitely wanting me and Tim to do it. I think it's a multifaceted, from my perspective, Tim will definitely provide his. It's a multifaceted, multivariable approach. I find that at some point, let's say above 100 kilos of sulfur, the capex and opex start leaning more towards treating in the biogas, and maybe at lower concentrations towards removing sulfur inside of it, but there's many different variables there. And both technologies, I believe, have very good spots there.
You mentioned the key phrase there, Timur. It's that comparison CapEx versus OpEx, and there's going to be operational considerations there. Can somebody actually operate the system? What's the scale of that system? Most of the cases we've seen, it's using both of those things in combination, and that's been a pretty happy strategy for most of the folks that have done that, both the iron and the scrubbing system. So.
All right. So in parting, George tells us that you guys rock. So you got that going for you. So thanks for the plug, George. Thanks everybody for joining. And thank you so much for the panelists for taking your time. This was good stuff. So over and out, everybody.
Paul, thank you.
My pleasure,
Thanks all.
Tim.
Bye-bye.